Hi, I'm Bob. Welcome back to our tutorial on how to solve the exercises for the textbook Microeconomics Theory and Applications with Calculus, the 5th edition. Today, we will solve the problems about option, behavioral game theory, and the challenge part. Here's exercise 4.1. It is about a second prize sealed bid option. Suppose Anna's value of the painting is $20,000. Bill's is $18,500 and Cameron's is $16,800. Each bidder's consumer surplus is the difference between the value and the price if he or she wins the auction and zero if he or she loses. The values are private. What is each bidder's optimal bid? Who wins the auction and what price does he or she pay? The bidder's optimal bids are their values on the painting. Anna bid $20,000, Bill bid $18,500, and Cameron bid $16,800. Anna wins the auction and she pays the second highest bid, $18,500. Her consumer surplus is $1,500. Let's solve exercise 4.2. It is about an English auction. Why did the value fluctuate substantially from night to night? Which bidder's bid determined the sales price? Why did the audience knowledge that the proceeds would go to charity affect the auction price? The bidders may be different each night, and they have various private values on the items. So the outcomes are different. The price the winner pays is the second highest bid. The fact that the proceeds would go to charity increases many bidders' private values, and therefore might raise the bids. Let's solve exercise 4.3. Charity events often use silent options. In a silent auction, bidders write down bids and submit them. Some silent auctions use secret bids, which bidders submit in sealed envelopes and which are confidential. Other silent auctions are open. Bidders write a bid on a bulletin board that everyone present can see. Which kind of auction would you expect to raise more revenue for the charity? In theory, they are equivalent. In practice, the open silent auctions may raise more revenue because bidders feel proud when they are seen making donations to charity and winning the bids. Let's jump to the behavioral game theory. Here's exercise 5.1. Draw a game tree that represents the ultimatum game in which the proposer is a first mover who decides how much to offer a responder, and the responder then decides to accept or reject the offer. The total amount available is $50 if agreement is reached. But both players get nothing if the responder rejects the offer. The ultimatum game can be represented in a game tree. The proposer makes an offer first, and then the responder decides whether to accept the offer second. We use the backward induction approach to find the subgame perfect Nash equilibrium. We first consider the responder's strategy in the second stage. Given that the proposer offers a rational minimum amount, say $1, the responder gets $1 if he accepts, but 0 if not. Her best response is to accept the offer. We underline her payoff 1 and add an arrow on the path. Given that the proposer makes a fair offer, like $20, the responder's best response is to take the offer. We underline her payoff 20 and add an arrow on the path. The responder's strategy in the second stage is to accept the offer, regardless of the amount. Next, we figure out the proposer's decision in the first stage, given the responder's responses. If the proposer offers the rational minimum amount of $1, she knows the responder will accept it and she will have $49. If she makes a fair offer, she will get $30. She is better off making the rational minimum offer. We underline her payoff 49 and add an arrow on the path. The subgame perfect Nash equilibrium path is that the proposer first offers the rational minimum amount, and then the responder accepts it. The outcome of the game is that the proposer gets 49 and the responder gets 1. However, the rational minimum amount offer is rarely made, and when it is usually rejected. One explanation is that the responder's payoff from accepting a low offer becomes negative because of a feeling of being insulted or an aversion to unfairness. After we change the payoff, we find that the subgame perfect Nash equilibrium path becomes the proposer first makes a fair offer, and then the responder accepts the offer. The outcome of the game is that the proposer gets 30 and the responder gets 20. Let's solve exercise 5.2. A prisoner's dilemma game is played for a fixed number of periods. The fully rational solution is for each player to defect in each period. However, in experiments with students, players often cooperate for a significant number of periods if the total number of periods is fairly large, such as 10 or 20. What explanation can you give for this behavior? From previous exercises, we know that the Nash equilibrium of the prisoner's dilemma game is that both players confess. It occurs when the game is played once or repeated for finite periods. If the game is repeated indefinitely, the players can use the trigger strategy to induce a cooperative outcome, and the joint payoffs can be maximized. However, experiments show that in a finite period prisoner's dilemma game, cooperation happens. The explanation could be that the students feel guilty if their confession causes the other player to be jailed for more years. That is why they choose not to confess. Another reason could be that experiments are experiments and not actual situations. Let's go to the challenge part of the chapter. Here's exercise 6.1. In the game between Intel and AMD in the challenge solution, suppose that each firm earns a profit of 9 if both firms advertise. What is the new Subgame perfect Nash equilibrium outcome? Show in a game tree. Suppose the profits change to 9 if both firms use high advertising. The backward induction gives the Subgame perfect Nash equilibrium. In the first stage, Intel sets high advertising. In the second stage, AMD sets high advertising no matter what Intel chooses. The equilibrium path is that Intel sets high advertising first, and then AMD also sets high advertising. The outcome of the game is that both get 9. Let's tackle the last problem. Derive the mixed strategy Nash equilibrium if both Intel and AMD act simultaneously in the game in the challenge solution. What is the expected profit of each firm? We write the payoff matrix. Suppose Intel sets low advertising with a probability of alpha. We calculate AMD's expected profits for each of its strategies. If AMD chooses low advertising, its expected profit equals the profit in each situation times the probability of that situation. That is 4 minus 2 times alpha. If AMD chooses high advertising, its expected profit is 3 plus 5 times alpha. AMD should be indifferent between its two strategies. Otherwise, it will choose one strategy with certainty, and then Intel will respond with certainty. Only when the two expected profits are the same can a mixed strategy Nash equilibrium exist. We obtain alpha, the probability at which Intel sets low advertising, which is 1 over 7. By symmetry, we can obtain beta, the probability at which AMD sets low advertising, which is also 1 over 7. Thus, the mixed strategy Nash equilibrium is that both firms set low advertising with a probability of 1/7 and high advertising with a probability of 6/7. Thank you so much for watching this video and solving all the exercises in this chapter. See you soon. Take care. Thank you for watching this video and subscribing to my YouTube channel. See you next time.